But first of all, it's my pleasure once again to welcome Naty Hoffman. So Naty first organized this course in 2010, and so we're really always really grateful to him for always helping us out find speakers each year. So Naty is the Vice President of Technology at 2K. So previously he was employed at Activision, working on graphics R&D for various titles, including the Call of Duty series. Sony Santa Monica Studio, so coding graphics technology for God of War 3. Naughty Dog, and developing PS3 first-party libraries. Westwood Studios, leading graphics development on Earth and Beyond. And Intel, driving Pentium pipeline modifications and assisting the SSE instruction set definitions. So he's got a long and illustrious history, and thanks and welcome, Naty.
Thanks for the introduction. Hi, so some of you may have seen this background talk before. I've done quite a few modifications to it this year, so hopefully it won't all be old hat. So, but one thing that hasn't changed is that over the next 15 minutes, I'll be going from the physics underlying shading to the math used to describe it. So what is light from a physics standpoint? It's technically an electromagnetic transverse wave, which sounds very fancy, but it actually means that the electromagnetic field wiggles sideways as the energy propagates forward. This wiggling in the electromagnetic field can be seen as two coupled fields, electric and magnetic, wiggling at 90 degrees to each other. Electromagnetic waves can be characterized by frequency, the number of wiggles they do in a second, or wavelength, the distance between two wave peaks. Now, engineers in various disciplines have to deal with electromagnetic wavelengths ranging from gamma waves that have wavelengths of less than 1/100th of a nanometer to extreme low frequency radio waves. Those waves are tens of thousands of kilometers long. And everything in between, but the range that we can actually see with our eyes is a tiny, tiny subset of that range, only from 400 nanometers for violet light to 700 nanometers for red light. Now, to give you a bit of intuition for what 400 to 700 nanometers actually is, because the physical size of this will become relevant later in the talk. So on the left, you can see visible light wavelengths relative to this sort of gray cylinder. That's a single strand of spider silk, which is 1 micron in width. And on the right, to give some extra context, you see that same strand of spider silk, how it would be relative to the width of a human hair. So, it's something that's very, very tiny, but still you can see a strand of spider silk with your naked eye, and these are fairly close to that, maybe half or a third of that in width. So far, what I've shown you are simple sine waves that have a single unique wavelength. And this is the simplest possible type of light wave, but it isn't at all a common type of light wave. Most light waves contain many different wavelengths with a different amount of energy in each. This is typically visualized as a spectral power distribution, or SPD for short, as you can see in the upper left. The SPD for this particular wave shows that this wave's energy is all in a single wavelength. It's all in a single wavelength in the green part of the spectrum. And this is typically what you will see in light emitted by a laser. So it's sort of a Dirac delta function in the SPD. In actuality, lasers actually have a little bit of bandwidth, but they are extremely narrow. Now, here we see the SPDs for red, green, and blue laser that are each multiplied by a factor and added together to produce the SPD on the right. Now, this kind of spectral power distribution is similar to what you would see in light from a laser projector. And laser projectors are starting to show up in higher-end theaters, newer theaters. They offer wide contrast, wide gamut. They have some advantages. So this is an extremely spiky spectrum, and still very simple. It's not one sine wave, but it's 3 sine waves. And if we look at the actual waveform, we can see that after adding up these 3 simple sine waves, we end up with something that maybe looks a little more complicated than a single sine wave, but not that much more so. You can see some underlying frequency, and there's some larger beats there. However, most light that you'll see in nature doesn't look like that. The SPD looks more like this. This is the SPD for D65, which is a standard spectrum for white light, outdoors light. And you can see also the waveform that it will create, which is, of course, very complex. Basically, the broader, the more detailed SPD, the more chaotic looking the waveform will be, and the less it will resemble a simple sine wave. Now, an interesting thing is that although these two SPDs could not be more different, one is extremely smooth and broad, the other one is 3 delta functions, but they have the exact same color appearance to humans. Now, the y-axis isn't to the same scale, so obviously the spikes are higher to compensate for the lack of width, but the fact that human color vision cannot distinguish between these two signals tells us that human color vision is incredibly lossy. It maps the infinite dimensional SPD down to a three-dimensional perceptual space. Now, if we look at this waveform, in vacuum it will propagate forever. The electric and magnetic waves will sort of reinforce each other and it'll just keep on going and going. But for rendering, what we care about is what happens when this light wave interacts with matter. Now, what happens is when an electromagnetic wave hits a bunch of atoms or molecules, it polarizes them. That means that it stretches this and separates the positive and negative charges and forms dipoles. This absorbs energy from the incoming wave, and this energy is radiated back out, you can imagine like a spring, and then the dipoles sort of snap back. And this energy is re-radiated outwards. And sometimes some of it is lost to heat, other times all of it is preserved and radiated outwards in new waves going in all kinds of directions. In a thin gas, the molecules are far enough apart that you can treat them individually, and then there are fairly simple physical and mathematical formulations to understand what's happening. But in other cases, in dense gases, liquids, solids, the combinations of the dipoles interact with each other and the waves interfere with each other. And the whole thing is, in the general case, much too complex to accurately simulate. So the science of optics, in this case physical or wave optics, in order to tame this sort of chaotic situation, they adopt certain abstractions, simplifications, and approximations. For example, they have the concept of a homogeneous medium through which light travels in a straight line. Now, a homogeneous medium is an abstraction, obviously, because matter composed of atoms can never be truly homogeneous at all scales. But in practice, this abstraction works quite well for materials that have uniform density and composition. The optical properties of this homogeneous medium is described by its index of refraction, or IOR for short. This is a complex, or in other words, a two-part number. One part of the IOR describes the speed of light through the medium, and the other one describes how much light is absorbed by the medium. And there are many media that are completely non-absorbent, and for them that number will be 0. Localized inhomogeneities in the medium, because you have to model things other than a completely homogeneous medium. So the way that optics models these localized inhomogeneities is as particles. So the assumption is that we have these abrupt IOR discontinuities, and they scatter the incoming light over various directions. This is similar to individual molecule polarization that we discussed earlier, but these particles can be composed of many molecules. And there are some formalisms in order to handle this situation. Again, it's a bit of an abstraction over what's actually happening. Now, the overall appearance of a medium is determined by the combination of its absorption and scattering properties. For example, a white appearance, like the whole milk in the lower right corner, is caused by high scattering and low absorption. You can sort of see absorption and scattering as two independent axes here. And if a liquid is colored, that just means it absorbs light more readily in some wavelengths than in others. So it's sort of spectrally selective. Now, we've briefly touched on participating media here, but actually the rest of my talk will be focused on object surfaces, which is a more common and basic case in rendering. Now, from an optical perspective, the most important thing about a surface is its roughness. No surface can be perfectly flat. At the very least, you have irregularities at the atomic level. Irregularities that are of similar size or smaller than the light wavelength, I will call this nanogeometry. And these cause a phenomenon called diffraction. There is something called the Huygens-Fresnel principle that can help understand diffraction in an intuitive way. It states that each point on a planar wave, you can imagine each point on a planar light wave is the center of a new spherical wave that's being emitted. And then these spherical waves will interfere with each other in order to create a new plane wave. Now, so far, this hasn't gained us anything in terms of intuition. We went from a plane wave through a bunch of sphere waves back to a plane wave. But where this sort of mental picture helps is when the wave hits an obstacle. And that's when you get diffraction. So when the wave hits the obstacle, then you imagine these spherical waves, and then one side of it, the spherical wave that's on the very corner of this obstacle, it doesn't get canceled out because there's no other waves next to it. And you see the light is kind of bending around the corner. It's actually not traveling in a straight line. And that's an example of something you don't get with the standard geometric optics. And the effect of this will be to slightly soften shadows. Even if you have a point light, your shadows will be very slightly soft due to this effect. Now, what's more interesting for reflectance, which is what this course is about, is diffraction on a surface, the irregularities, this nanogeometry that's on a surface. And for this case, I'm going to look at an optically smooth surface. An optically smooth surface is defined as a surface where all the irregularities are in the nanogeometry category. So all the irregularities are smaller than the light wavelength. It's actually not hard to polish a surface to that degree. Commercial glass is commonly polished far smaller than a visible light wavelength. And if we look at this plane wave hitting this surface that's irregular on a scale of tens or hundreds of nanometers, then we can apply the same Huygens principle. And so we see that every point on the surface is emitting its own spherical wave, and this looks a bit chaotic because it is. Some of these surface points are higher, some of them are lower. That's due to the nanogeometry. And then all of these sphere waves will sort of interfere and reinforce each other, destructive and constructive interference, and you'll get this kind of complexly structured wavefront. This little drawing actually doesn't do it justice. And you'll end up with some amount of the light scattered in all kinds of directions. Now, the smaller the nanogeometry, the less light will be diffracted, and the more of it will be reflected sort of in the regular specular way that I'll talk about soon. So it's really a function of the height of the bumps. And if you have a surface that's, I think the term is super polished. I don't know if that's a technical term, but I've seen it used on several websites. It is possible with some effort and expense to polish a surface to the level of individual atoms. Then the scattering that happens on a surface like that will be small. It'll be on around 1% or 0.5% of incident light, but it's definitely still measurable. So there's no such thing as a perfect surface. Now, we're going to take a break from wave optics and move into the more familiar geometric or ray optics, which is a more simplified model, and it's really the model that all of computer graphics, with a handful of exceptions, has been using since forever. One simplification we'll make is to ignore nanogeometry. Basically, as far as geometric optics is concerned, if it's smaller than a light wavelength, it doesn't exist. Any optically smooth surface we'll treat as this mathematically perfect, abstract, flat surface. Now, it can be shown from the equations governing electromagnetic waves that such a perfectly flat surface, ideal surface, will split light into exactly two directions: reflection and refraction. Now, most real-world surfaces aren't optically smooth, but they have irregularities at a scale that's much larger than the light wavelength, but still smaller than a pixel. So we will call this microgeometry, to differentiate from the nanogeometry that was smaller than the light wavelength. And this microgeometry variation, it doesn't cause diffraction. What it does, it simply is tilting the surface in various directions. And since, as we saw here, both the reflection and refraction direction depend on the surface normal, on the surface orientation, then the microgeometry is simply changing the local normal at a very small scale. And you end up with reflected rays, even though each specific point on the surface is only reflecting the incoming light into a single direction. Because a pixel covers a lot of bits of surface angled in different directions, you end up with this sort of statistical aggregate. Now, this is roughness on the microscopic scale. If I look at these two surfaces, then to our eye they seem equally smooth. They seem like these nice, smooth hemispheres. One has a hole in the middle, but other than that, they're very similar shapes. But on the microscopic scale, they're different. The top surface is slightly rough. If you took a micrograph of it or microphotograph of it, you would see these sort of gently undulating hills, as it were. And that means that incoming light rays will hit surface points that are angled slightly differently and will bounce out in slightly different directions, and you'll end up with this sort of narrowish cone, and that's why the reflections are only slightly blurred. The surface on the bottom, however, it is on the micro scale very rough. If you looked at it in a microscope, it would look like the Alps or something. And so every bit of surface hit by the light is angled in a very different direction, and the light spreads out in a very wide cone. Now, in the macroscopic view, we don't model the microgeometry explicitly. We treat it statistically and view the surface as reflecting and refracting light in multiple directions in a cone. And the rougher the surface, the wider this cone will be. Now, the question is, we've talked about reflected light, but what happens to refracted light? And this depends on what kind of material the object is made of. Since light is composed of electromagnetic waves, the optical properties of a substance are closely linked to its electric properties. And we can group materials into three main optical categories: metals or conductors, dielectrics or insulators, and semiconductors. And you really, in games and in movies, you don't see a lot of exposed semiconductors lying around. So we can, in most cases, ignore that situation and just divide everything into metals and non-metals. That has the advantage of being way more intuitive to an artist than talking about dielectrics and the like. Now, metals immediately absorb all refracted light. Basically, there's this sea of free electrons. It sucks up all the electromagnetic energy, and it's gone, never to return. Non-metals, however, behave like those cups of liquid we saw earlier. Effectively, you have this participating medium underneath the surface that the refracted light is participating in. And the refracted light is scattered or absorbed or scattered and absorbed. You have all the same variations we saw in those cups of liquid. If the object is made of a completely clear substance like glass or liquid, the light will just keep on going. But if there's enough scattering, which most objects will have, some of this refracted light will be scattered back out of the surface. And those are the little blue arrows that you see coming out of the surface in various directions. And I've kind of tried to visualize the fact that the light internally is getting selectively absorbed, so it's getting tinted blue. So the arrows are sort of, the yellow arrows turning bluer and bluer and bluer until they get back out of the surface. Now, this re-emitted light comes out at varying distances from the entry point, and you can see the yellow bars show one ray is coming out really close to the entry point, one ray is coming out a bit farther. And this distribution of distances depends on the density and other properties of the scattering particles. Now, if the pixel size or shading sample area or distance between shading points or shading rate or however you conceptualize that, but just sort of the area of interest for shading, if that pixel size is large, like the red bordered green circle in the image, compared to the entry-exit distances, then we can assume distances are effectively zero for shading purposes. We can't resolve the fact that the light is coming out in a different point that it's entering. So in that case, by ignoring the entry to exit distance, we can compute all shading locally at a single point, and the shading color is only affected by light that's hitting at one point. It's convenient to split these two very different light material interactions into different shading terms. So we tend to call the surface reflection term specular, and the term resulting from refraction, absorption, scattering, and re-refraction we call diffuse. Now, in the other case, where the pixel is very small, or small compared to the entry-exit distances, so we have the red bordered green circle again, but it's much smaller in this picture compared to the scattering distances, then we can't treat the shading as all happening at a single point. We need some special subsurface scattering rendering techniques. And even regular diffuse shading, the physical phenomenon is the same. It's still subsurface scattering. The only difference between something where you're running a subsurface scattering shader and one where you're running a regular diffuse shader is the difference between the shading resolution and the scattering distance. So it's not true to say that this material is a subsurface scattering material because it all depends on the distance to the camera, right? If you have plastic from far away or from arm's length, then it acts like diffuse. But if you're looking at it super up close, like in the Lego movie, then you can see visible diffusion happening. And the same thing happens in reverse. If human skin has visible scattering behavior, but if you're looking at a human from far away, you can just shade them with a BRDF. Now, so far we've discussed the physics of light-matter interactions. Of course, to implement them in a game or film render, you have to turn these physics into a mathematical model. And the first step is to quantify light as a number. Radiometry is the measurement of light. There are many different radiometric quantities that are integrals over direction, over area, but we'll mostly use radiance. And radiance measures the intensity of light along a single ray, and it is spectrally varying. Now, radiance values are properly expressed like SPDs, like the ones I showed earlier in the talk. And later in the course, you'll hear about Weta Digital and how they do proper spectral rendering where they're looking at the whole sort of spectral distribution of energy. However, for the rest of this talk, I'm going to follow traditional film and game usage, and that is basically to use RGB for anything that's spectrally varying, like radiance. Now, the units of radiance are watts per steradian per square meter. Now, since we are using the assumption that shading can be handled locally, we're sort of taking the subsurface scattering case out of the scope of this particular talk, then light response at a surface point only depends on the light in view directions. And since you can parameterize each of those with two numbers, then you have this four-dimensional function, which we call the bidirectional reflectance distribution function, or BRDF. And that's a function of light direction L and view direction V, as I said. In principle, it's a function of these 3 or 4 angles. It's 3 angles if it's isotropic, but in practice, there are various different ways of parameterizing BRDFs, and with various advantages and disadvantages to them. Now, note that the BRDF is only defined for light and view vectors above the macroscopic surface, and I talk a little bit more in the course notes about how to handle other cases. Now we come to the actual math. This is the reflectance equation, and it may be somewhat scare-looking if you're not of a mathematical bent. Let's say you have a more artistic background, but basically what it's saying is that outgoing radiance from a point equals the integral of incoming radiance times the BRDF times the cosine factor over the hemisphere of incoming directions. I'm sure that doesn't sound much more reassuring, But if you're not familiar with integrals, you can think of it as a sort of weighted average over incoming directions. So all I'm really doing is I'm taking all the light coming in, I'm using this BRDF to kind of average it, so I'll give more importance to some directions, less importance to others, and just adding it all together. And this X and circle notation, it's not a standard notation of any kind, but it's one that we used in our book, Real-Time Rendering, and since we didn't find an alternative, we just stuck with it. It means component-wise RGB multiplication as distinguished from simple scalar multiplication. Now, we'll start by looking at the surface or specular term. In this figure, it's denoted by these orange arrows that are reflected back from the surface. And we will be looking at it through the lens of microfacet theory. Microfacet theory is a way to derive BRDFs for surface reflection from these non-optically flat surfaces. And the assumption behind it is that we have a surface with detail that is small compared to the scale of observation, but large compared to a light wavelength, which is how we defined microgeometry. And in that case, each point is locally a perfect mirror. Remember, we said that with geometric optics, we're ignoring nanoscale irregularities, or assuming that anything under the wavelength of light is like this mathematically perfectly flat plane locally. So each point is locally a perfect mirror, and as we've seen, a perfect mirror will reflect each incoming ray of light, ignoring refraction for the moment, into one outgoing direction. And that outgoing direction depends on the light direction and the normal. In this case, it depends on the light direction and the microfacet normal. Now, only those microfacets that happen to have their surface normal M oriented exactly just so in order to bounce L into V, only those will reflect any visible light, right? Any microfacet that's aiming in even a slightly different direction will be bouncing L into some direction that's not V, and will not contribute to the BRDF. So this direction where is the half vector H, and the half vector H is very common in physical shading models, but it's important to note that this is its actual meaning. The half vector H is very simply the direction in which the microfacets need to be pointing. Now, not all microfacets that have M equal to H will contribute. Some will be blocked by other microfacets from either the light direction, which we call shadowing, or the view direction, which we call masking. In reality, blocked light will continue to bounce, and some of it will eventually contribute to the BRDF. Microfacet BRDFs ignore this, so effectively they assume that all blocked light is lost, and we know that's an error. We just live with it for now. Now, this is the form of a general microfacet specular BRDF. You can derive it based on the assumptions I just described. And it has a sort of component structure to it, which is useful. I'm going to explain each part individually. Now, this particular expression is the Fresnel reflectance. It's the fraction of incoming light that is reflected, as opposed to refracted, from an optically flat surface of a given substance at a given lighting angle. And it varies based on the light angle and on the surface normal. So Fresnel reflectance tells us basically, remember I said only certain microfacets are relevant, the ones with their normal equal to H, and those microfacets behave as a perfect mirror. So what this expression tells us is of the light hitting each of those perfect mirrors, what percentage is reflected. Now, you can graph this for a given material. You can graph this as a function of the angle of incidence, which is the angle between the incoming light ray and the normal in this case is M, and the M in this case is H. We don't care about the microfacets for which M is not H. And some materials here have one line in this graph, like water, diamond, iron, and glass. And some of them have three. The ones that have three, the three lines are simply showing the R, G, and B channels and how they vary. And I didn't distinguish them here, but for copper, the high one is R and the low one is B, and for aluminum, I think it's reversed. Now, if you look at Fresnel reflectance, then you can see that it has a very specific kind of behavior. So if we look at an optically flat surface, the relevant angle for Fresnel reflectance is the one between the view and normal vectors. And we can see, here I'm visualizing the Fresnel reflectance of a teapot, and we can see that it has a very dark reflectance color in the middle, and it brightens to white at the edges. If we look again at the graph, we can see that we can divide into sort of three zones. So we start out at the angle of incidence 0 on the left side of the graph, and then it has this sort of constant value, and as the angle of incidence increases, you can see the lines within the green zone remain basically flat. So the green zone is the zone over which the specular reflectance doesn't really change. And then in the yellow zone, it starts changing slowly, and in the red zone, it changes abruptly and goes to 1. And you can visualize those same zone colors over a 3D object, so you can see that the vast majority of visible pixels are in the areas where the reflectance either doesn't change or barely changes, and there's only a very small number of pixels that are exhibiting this rapid increase to reflectance of 1. Now, since over most of the visible surface, the Fresnel reflectance value is similar to the value that it has at 0 degrees, then it's a very useful anchor to treat this value as the characteristic specular color of the surface in general. So we take the value of Fresnel reflectance at 0 degrees, and we just call it the specular color of the material. And we can calculate that. It has a physical meaning, and it can be calculated from known physical constants. As I noted earlier, it's useful to divide substances into metals, dielectrics, and semiconductors. And here we see a bunch of metals. And metals, as a general rule, they have bright specular. With one exception, the gold-blue channel surrounded by this red circle here. There's no value in this table below 0.5, or at least not much below 0.5. And most of them are much higher. And besides linear values, we also have a column for 8-bit sRGB values, which is what an artist would paint into the texture. And we also visualize the color. And since metals lack subsurface scattering, as we said, they just swallow up all refracted light, then all the visible color of the metal is the surface reflection or specular color. Now, some metals are very strongly colored. Gold is a bit of an outlier in two ways. Its blue channel is unusually low, and its red channel is unusually high. In fact, its red channel is actually outside the sRGB gamut. So I show the value here, which is 1.022. In practice, you would just clamp that to 1. Now, the fact that gold is so unusually strongly colored for metals probably contributes to its unique cultural and economic significance. Despite its low blue value, gold is also one of the brightest metals. This table is ordered by lightness, CIE-Y coordinate of specular color. And you can see that among these metals, at least, which are sort of a bunch of common metals, elemental metals, gold is like the third brightest. Now, on the other hand, dielectrics have dark specular colors, and they're achromatic, uncolored, which is why this table I'm giving single values or ranges, but I'm not giving RGB triples. And dielectrics typically will also have a diffuse color, a subsurface scattering color, in addition to the specular color shown in this table. So unlike metals, this is not the only source of surface color. Now, in this table, I'm going to group common dielectrics into categories of increasing F0 values. So we start with water, which at 2% is sort of the darkest specular reflectance you're likely to see outside some custom anti-reflective coating. And common plastics and glass, and as I'll mention later, a whole bunch of other things are in this sort of 4 to 4.5% range. I would look at the linear column because that's the amount of light actually reflected physically. And then we have decorative substances that are decorative precisely because they are very shiny and have bright reflectance, like crystalware and gems. And finally, we have diamonds and things that are used as replacements for diamonds, ranging from Swarovski crystals to moissanite, which is actually brighter than a diamond. And so it goes from like 2% all the way up to 20%. But you notice that the lower you go on this table, the higher the numbers get, the sort of rarer the materials get, and the less of them you'll see in a given scene. Since the vast majority of dielectrics that you'll see in practice fall sort of into the plastic glass row of this table, it's not unusual in many engines or texturing systems to just set a constant dielectric color of 4% and call it a day. Now, what about semiconductors? As you would expect, they're in between. They tend to have F0 values in between the brightest dielectrics and the darkest metals. And we use silicon here as sort of a proxy for semiconductors in general. Typically, like I said before, you don't just have big blocks of silicon lying around in most game and movie scenes. And practical purposes, I recommend treating the range of F0 values between 20 and 45% as a kind of forbidden zone where materials won't go into that zone unless you're trying consciously to do some kind of exotic effect. Now, we've talked about how to get the value for 0 degrees, but we do need to model the angular variation in some way, and everyone has been using the Schlick approximation pretty much forever, though there are some more optimized math expressions that have gained some popular use in recent years. But the nice thing about it is it's fairly accurate. I don't have a graph here comparing the two, but if I did, you'd see that it stays reasonably close over most of the range. It's quite cheap to calculate, and more importantly than all of those properties, it's parameterized by F0, because the original Fresnel math is parameterized by spectral indices of refraction, and spectral indices of refraction is not the kind of thing you want your artist worrying about. So F0 is a nice color, it's RGB, it's 0 to 1, it has very intuitive meaning, and it's a much better thing to parameterize by. And then depending on whether you're doing sort of a mirror reflection or a microfacet BRDF, you just plug a different normal in, either N or H. Now, the other chunk in this sort of Lego expression is the normal distribution function, or D. And we evaluate it for the direction h because, as we said, h is the direction that the microfacets need to point for us to care about them, for them to contribute. And we want to know how many of the total microfacets on this surface are pointing in that direction. So that's why we're evaluating this normal distribution function. And that's a function that will just tell you for any direction you give it what's the sort of concentration of microfacet normals that point in that direction. And then NDF intuitively determines the size and shape of the highlight that you'll have. Now, the course notes go into great detail on all kinds of options for NDFs. And they mostly fall into two main classes. The sort of more historically used ones are the Gaussian-ish ones, Beckmann, Fang. They all have this sort of overall Gaussian appearance. They have blobby highlights. And then GGX, or more properly Trowbridge rates, has slightly different appearance. It has more kurtosis. It has this spiky center and these sort of long tails. So the appearance of the highlight is more like a sharp highlight surrounded by kind of haze or a halo. Now, there are many surfaces that are not well represented by such smooth functions. I'll show some images from last year's glint rendering paper by Jan et al. Production BRDFs, normal map filtering techniques tend to use smooth lobes, either isotropic smooth lobes or anisotropic smooth lobes. And those are good models for surfaces where the microgeometry is much smaller than the pixel, where the pixel is covering tens, hundreds of thousands of bumps, and they all get nicely smoothly averaged together. But there are many surfaces of interest for which maybe the pixel's covering dozens of bumps, and much less than tens of thousands, and then you don't get this nice statistical averaging. You get something that looks like this. And that's obviously very different. Trying to model this with this blob is going to lose you something. And what you lose is this characteristic glinty appearance that the paper was addressing. Now, the solution in the paper looks, at least to my sort of not film expert eye, as something you could use in film production. It's definitely too costly for games. Games at the moment use more ad hoc methods. If anyone attended the Advances in Real-Time Rendering course on Monday, there was a snow sparkle talk. That's a good example of the kind of things that we do in games for this sort of effect. Now, one other thing which is also highlighted by images from a recent paper, it's important to account for the effect of surface deformation on NDFs. And this is something that is usually ignored and not modeled. The following images are from the skin microstructure deformation paper by Nagano et al. And it's going to be presented at the appearance capture session this afternoon. The left side I'll show a series of images, and the left side will show a patch of skin which is undergoing varying amounts of compression and stretch. And the NDF of that patch of skin is on the right. And you can see that as the skin goes from compression to relaxation and then to stretch, the shape of the NDF changes quite a bit. And although the paper was talking about human skin, in principle, you'll have this type of behavior with any flexible surface material that has some microstructure to it. So this is something that in theory we should be modeling whenever we're skinning something. In practice, I don't think many people are. So this is definitely an unaddressed area. So finally, we have the geometry or shadowing masking function. That's the last part of the BRDF. I mean, the rest are just dot products. They're basically reprojection factors. And this is the geometry function, or sometimes called the shadowing masking function. And D gives us how many microfacets, what concentration of microfacets do we have pointing in the right direction. F tells me how reflective they are. And G tells me how many of them are unshadowed and unmasked, so they are actually transferring light from the L direction into the V direction. And it basically gives us the chance that a microfacet with a given orientation is lit and visible. Now, there are many different options in the literature for the geometry function, but there was a very good analysis of this function and its meaning by Eric Haitz, which I strongly recommend reading for anyone who's interested in this area. And he showed that only the Smith function, the uncorrelated form of which is shown here, is both mathematically valid and physically realistic. Now, there are further details about this, and there are also various other forms, various correlated or partially correlated forms of Smith that can be found in Heitz's paper. So this is basically the function you should use. Now, if we put it all together, we see that the BRDF is proportional to the concentration of active microfacets, which are the ones with normals aligned with H, times their visibility, times their Fresnel reflectance. The rest of the BRDF in the denominator consists of correction factors related to the various frames involved. Now, I'm running a bit late, so I'll skim over the diffuse part, and which is the subsurface term. So people have traditionally modeled this with Lambert, which is a constant. The n.L is part of the reflectance equation, not part of the BRDF. And there are various models going beyond Lambert. Some of them we've seen in this course in previous years. Some of them model this diffuse specular trade-off, whereas Fresnel is causing more light to go towards a specular. That means that necessarily it's causing less light to be refracted and less light to be available for the diffuse model, which Lambert does not model. And there's also BRDFs that take account of surface roughness. And that's something that I really wanted to stress a particular point here, that taking account of roughness for the diffuse reflectance is a good thing to do, but you have to be very careful in how you do it. It depends on whether the surface has microgeometry that's larger or smaller than the scattering distance. And that's when you pull out the models like Orenayar or Disney Diffuse. And there's this common pattern I've seen where people just use this roughness-based diffuse on all of their materials, and they just plug in the specular roughness into the diffuse roughness. And I think that's really not a good approach, because it's been known for a while that the diffuse response effectively smooths out small bumps. If you're familiar with ICT's light stage, they give you separate normal maps for specular and for diffuse. So if you look at something like human skin, the specular normal map will be very have lots of high frequency detail, and the diffuse normal map will be sort of smoother and more filtered. Effectively, the diffusion profile filters out the normal map, and everybody, or a lot of people know that, but it seems that a lot fewer people know that this applies even more so to the roughness. And ideally, you should have a completely separate roughness for diffuse and for specular, because it's not a simple factor. You can't say, okay, my diffuse roughness is half or a third, because it really depends on the size, right? You don't know how big the bumps are. The NDF doesn't tell you that. So otherwise, I'd recommend just use them sparingly. Don't have them be the default. Use them in cases where you know the material has this property that the roughness is very coarse compared to the scattering distance. And I'm sure you thought I completely forgot about wave optics, but it's back. Dun, dun, dun. And turns out that it is actually important. We've all been ignoring it for, I don't know, 30, 40 years, with a handful of exceptions like Hay et al. In '91. And we've either ignored the effects of nanogeometry diffraction, or we asserted their insignificance. But at the recent Material Appearance Modeling Symposium in June, which I sadly missed, Holchu and Pakanowski showed pretty convincing evidence that part of the visible BRDF behavior, the long tail of the highlights in particular, was due to this phenomenon that we've been blithely ignoring. Now, for more detail, I recommend looking at the talk slides that are online, but I'll just go over some high-level differences between the two. So it appears that in many materials, reflectance is affected by roughness on both the micro and nano scales. The micro scales is all the stuff we've been talking about. The lobe shape is determined by the surface statistics. It turns out that nanogeometry, the lobe shape, is also determined by a completely different surface statistic, which is the surface roughness SPD, which is the same SPD we saw in the beginning, but applied to 2D spatial properties rather than 1D time property. Microgeometry has no wavelength dependence. Nanogeometry reflectance has a strong wavelength dependence. In both cases, the incident angle can affect the effective surface statistics due to different effects. Now, of course, all this math needs to be turned into rendering implementation, which I'm not going to talk about now, but basically all the other talks in this course, both this year and previous years, are at least partly about that. And I'd like to acknowledge people who have helped me with this talk, and to end on a note that we are hiring. We have open positions at many of our studios, and personally, my Central Tech department is looking for some top-notch rendering and engine programmers. Okay, thank you.